looks like. What is a computer? Do you like my animation? I worked a lot to make this nice animation. What is a computer? Essentially, I open the question again. What is the difference between the two things? One is a telephone, the other is a telephone. What is the difference?
One of them is smart. So one of them have computer, so it is a smartphone.
Okay.
The other one is a regular phone.
Okay, and what is the practical difference between okay, one is the way they make is different, but what's the difference between a telephone with computer and a telephone without computer?
One of them only can make calls, the other one do everything that a computer can.
And what is the old thing that the computer can? It's a good answer, by the way.
They can have a data and can produce it.
So that is the basic idea. The old telephone can do one thing, be telephone. The new telephone can be camera, can be TV, can be, I don't know, Telegram, online lesson. You can. Some people are watching this lesson in the telephone. Yes. Just imagine this. I don't know, because you are very young, you don't know. But when I was your age, I lived in Chile and I have family in France. And we managed to call them once every month because it was super expensive. Let's say $100, $200 to speak for 10 minutes, long distance. And by a very bad telephone. Today, with the internet, I talk to my family almost every day with video. I see them with very high quality for free. If you told me 30 years ago that I will be able to talk with video at any price, not that. If you told me that rich people have a telephone with video, I will say this is impossible because the technology of the time was impossible. Today you have online video for free. It is this is the future. We are living in the future. So what can we do with a computer? The difference, the answer is correct. The answer is that computers, the new telephones are a computer, and computer can do more things than telephone. They can even speak by telephone. It's a camera that can speak by telephone. It's an internet browser with telephone. Computers initially were made to calculate formulas, to solve most of the equations. For example, to weather prediction, to calculate the weather. Also, used for store. And the key point is not to store data. The key point is to find it later. We can always store data. People store data in the libraries forever. But finding the data later, that is the hard part. To find patterns in data, that is the basic idea of science, to find patterns. To find data matching a pattern and to transform data in useful ways. So it's not only about holding data, is also to look into the data, to find patterns in the data, and to handle data. One trick of having data is that we can compress it. The reason why phone long distance calls are cheap or free, the reason why I can talk to you now is because my signal are compressed very efficiently, and we can send online because that is compressed. If we don't compress, maybe we will talk about this later, but if we don't compress, this will not work. Compressing data is one of the reasons why computers are super, super useful. One of the reasons why cell phones are much better than regular telephone. The other trick is that since data is digital, is that when I take the data and store in a file, and I give to you, you get exactly the same. Let's say this. Maybe you get a paper and you need to make a photocopy. And you want later, for some reason, to make a photocopy of the photocopy. And then you have a photocopy of the photocopy of the photocopy of the photocopy. What happens when you have 10 photocopies? What happens? You get a very bad quality. Isn't so? The photocopy of the photocopy, it get worse and worse every time. So the photocopy is not 100% copy. But if I give you the PDF file and you make 10 copies of the PDF file and then you make more copies of the copy, every time you copy a PDF file, you get exactly the same with zero change. That is another super important effect, super important factor that helps computer to be so successful. When we have digital data, it doesn't degrade. We can copy forever. So I Google or I look in my dictionary what computer mean, and they say it's an electronic device. Today, computers, historically, computers were different, but today, when we say computer, we understand an electronic computer with that work with electricity, let's say, that you use for storing and processing data according to instructions given by a program. And this is the key point, that the thing that you do depends on what we call a program. And the program can be changed. So the same machine that you make to speak by telephone can be used to watch YouTube, or can be used to write a novel. Or I mean, you can use it in the lab. There are many apps that allow you to use the cell phone in the lab. You can, I don't know, take picture of your Petri dish. So in summary, a computer is a general purpose device. It's not a specific device. It can do many things. And that is done with following a program, and the program is stored in the memory. So a key component of the computer is the memory. That is what I want to talk about now. The computers have several parts. The most important part, for my point of view, is the memory, because it's where you store the information and you recover it later. And the programs are also stored in the memory. That was the clever idea, that the very old computers, let's say the 19th century computer, you can store some information, but the program was not in the computer. You have to kind of physically change the computer. Now you don't change the computer, you just change the software, the program. So I always like to make this comparison, because as you know, in Turkish, we don't say computer. In Turkish, we say something that is between French and English. The English name for computer puts the point on the mathematics of this, in doing computation. Computation literally means calculator, okay? The French puts emphasis in storing and retrieving data, in sorting data. And the Turkish has both ideas. Has the idea that you count, but also the idea that you keep information. And I like this idea that we put both issues together. But at the very bottom level, a computer is a counter, a thing that handles numbers. We can store numbers, find numbers, and calculate things with numbers. So the key idea is that number will represent information. Computer can transform and translate information. Transform means sorting and doing mathematical operations. We will see some of them. Take an average, for example. It's something that we do often. And transfer, wrong error. Transfer, this is an F. Transfer, meaning that you can move the data very efficiently. You, of course, don't know, but before computers, if you want to read a paper, you have to buy a physical book. And if you didn't have money for the book, you had the option of writing a letter to the author of the paper. And the author had some copies of the paper. And if they like it, they send you back by regular mail a physical copy of the paper. That takes months. So if you want to read a paper, you send a letter, and 1 month later, if you are lucky, you get the paper. Now you download the PDF. So in 5 minutes, you could do what we did in 5 months. You will say, or some people will say, I don't use numbers. I am a letter person. Well, numbers are letters, but okay. Don't worry. Numbers, the basic idea is that you can see the pattern here, that numbers represent things. The key word of today is representing. So numbers are numbers, but number can represent things. What we call representing, for example, when we write in any written language, let's say, well, not all languages are the same, but let's say in Turkish, in English, in Spanish, or even in Arab, the symbols that we put in paper represent sound. So I say A, I say O, I say E, I say N, I say H. All these sounds are represented by symbols. If you play music, you also know that you can represent sound by symbols. Chinese is interesting because instead of representing sounds, they represent ideas. So this symbol, you can Google them if you like. I Google them, of course, I don't speak Chinese. They essentially represent something else. So if, and let me tell you, we have been doing this for at least 10,000 years. We know if you go to the museum here, the archaeological museum, you have seen a document that are, I don't know, 4,000, 5,000 years old, and they have symbols that represent sound and represent ideas. So information technology is old. We have been doing information technology for thousands of years. The difference now is that instead of representing them in paper, we represent them electronically with numbers. Example, sound is usually, for example, the microphone that I'm using now, or if you have a CD or an MP3 or whatever, is initially sound waves pressure in air that are transformed to electricity with a microphone, and that electricity is transformed into numbers. Typically in a CD, in a compact disc, you got 44,000 samples per second, and this sample get to transform into a number. Every sample is a level here. So you have higher pressure, you have a higher number, lower pressure, lower number. So this graphic, that is a real sound, is stored as a series of numbers. That's how CD work. And if you know something about music, you know that CD has much less distortion than the classical method like tape or vinyl. So people like the distortion, but it is sure that the distortion of the CD is less. You have pictures like this one. This is a grayscale that I show just because it's easy to understand. This well, we call black and white, but technically it's gray. You have black, you have white, and you have something in between. How we represent this? How we can take this picture and make it with numbers? Essentially, every point has a value between 0 and 255. Why 255? I will tell later. Every point is called a picture element or pixel. So every, for example, here you see the number 8 is a very dark number, and the number, I don't know, 96 is a gray level, and 248 is almost white, and white is 255. So here you get an idea how the numbers correspond to gray levels. So if we can transform every gray level to a number, we can have a picture like this. And if we want to do in color, what people realize is that you can make any color, not any, but enough for practical application. We are fine with 3 colors, red, green, and blue. And each one of them is stored separately. So instead of one matrix, we have 3 matrices, every one with a number between 0 and 255. So for example, here you have this picture. So sound pictures are transformed into sound. Pictures, for example, you may have heard about microarrays. Microarray, and there are some, not all, but there are several techniques in molecular biology that end with a picture, either from a microscope or a scanner, a cell counter, or you do FISH, you do hybridizations, and your output is a picture. So handling picture is one of the things that we can do in molecular biology, and it tends to be useful. So number can represent many things, can represent images, audio, movies. I didn't explain, but you can imagine that a movie is a series of pictures compressed efficiently. Naturally, it can also represent sequences, DNA, RNA, proteins. All these kind of sequences can be represented with numbers. You have 4 DNA bases, you have a number 1, 2, 3, 4. The structure of proteins is essentially given by the position of every atom, and the position is given by the X, Y, Z coordinates. So if you have the coordinate of the atoms, you have the structure of the protein. So numbers again. concentration of molecules. Every time you do PCR or qPCR, let's say, or many experiments, let's say metabolomics or transcriptomics or so, you will get numbers that measure concentration. The numbers, I don't need to tell you, are concentrations are numbers. At the end, all kinds of experimental results can be represented in numbers. And to be honest, sometimes you cannot. But if you cannot represent with numbers, we hardly can do anything. So, for example, people working in psychology, sometimes they have problems how to represent emotions. It is kind of complicated. What people do at the end is they assign numbers manually. Papers and PDF and publication, they are also documents. The document that we can represent with numbers. In summary, the point is that we care about computers because computer handle information. The information is encoded with numbers, so we will care about numbers, but the real reason is not the numbers. The real reason is the information carried by the number, the information represented by the numbers. Okay, so now I need to tell you about the part of the computer because there is some relevancy there is something that will be relevant for our work. Okay. First, you probably hear, but if not, because I'm sorry, let me just a parenthesis. Part of the goal of this course is not only to teach you how to use a computer, but also to have kind of general culture about computer, to know a little about the history, to know a little what it is. Even if you are never going to use a computer in your life, it's very hard, but let's say that you are never going to use a computer and you decide to be, I don't know, a musician or a philosopher, you cannot go by life without knowing what is a computer. It's so much important about our everyday life that any well-educated person should know this thing. You cannot go by life without knowing what is software, what is hardware. Even if you don't do software or you don't do hardware, you should know what is software, what is hardware, because they're essential part of our culture, of what we do in the universe, in the world today. So hardware is the physical part. Hardware is an old word for nalbur, let's say. Hardware is all the metallic thing or the physical thing that you can if the computer fail, you can punch the computer. The hardware is the part that you can touch. You can say, "Ah, damn computer," and you can push the hardware. But computers have a second part that other machines don't have. They have a part that is not physical. They have the software, the soft part. So hardware is an old word, and they have this hard part. So people invented the word software, that is a new word, meaning the part that is not hard, the part that is not physical. So the software is the part that you cannot touch. In some sense, it's like the difference between body and soul. The hardware is the body and software is the soul, in some sense. A more correct analogy is the biology. In a cell, you have all kinds of molecular elements. That is the hardware. The DNA, the molecules of DNA are still hardware, but the order of the molecules, that is software. I mean, everybody, you and me and everybody, got the same general shape of the chromosome. Your chromosome and my chromosome have essentially the same number of nucleotides, and they have essentially the same kind of nucleotide. You have A, C, G, and T. The difference between us is the order. Some minor change, but that change is enough to make everybody a different person. That is the software. The part of the computer well, it can be done in a different order, but I will say the traditional way. You start with the central processing unit, the CPU. Some people think that the CPU is a big box. That is not true. The CPU is a small electronic circuit. It's like 3 by 3 centimeters, very expensive. It's one of the most expensive things per kilo. It's like 10 grams and you pay, I don't know, $500. And it's called the central processing unit because essentially it's at the center of everything and it connect with every other part. First, it connect with people. If the computer doesn't connect with people or with the world, we don't care. Why you care about a computer that is not doing nothing? If there is no interface with the world, you will see sometimes the word interface, and you will see the word input output. I/O here means input and output. These are the keywords that people see around. Interface here, face is your face, the top of your head. So interface is the part that has two faces, one face looking inside and one face looking outside. In our case, the interface, in my case, for example, is the mouse and the keyboard. In the telephone, the interface is the screen, the speakers, and the screen is input and output. And the speakers are output, the microphone is input. That is interface. Then the most important part, in my point of view, is the memory. Now, I will tell you there are two kinds of memory. The first kind, the primary memory, is also called RAM. You will hear that. I'm telling you these words not because we are going to use them, but because you should know them. It's part of the culture to know what is RAM and what is not. RAM, if you see this is an electronic device. Maybe next time I will show you. I don't have it at hand, but one of these days I will show you some physical, if I have. I don't know if I have here. Anyway, so it's an electronic device that is connected to the central processing unit. So let's say you write a number or you write a letter, and essentially that information is going to the processor, and the processor is storing that in the memory, and eventually it can take it back and show you in your screen. Okay, so that is the basic movement of information from. And to be honest, my first computer was only this. I had an interface, very basic keyboard and some display, like a calculator, like your calculator, for example, the calculator that we use to calculate numbers, to calculate, to take average or so. You have a keyboard and you have a display with numbers, and there is some memory that you can store some limited amount of things, and a processor. But what happened is that this memory is limited. It is, let's say, this memory is very fast, but very expensive. And correctly, fast, expensive, therefore you don't have a lot, and it's also electronic, meaning that when electricity fails or when you turn off your computer, you lose everything. Therefore, you need a different way to store information. Believe me, when I had my first computer, I didn't have any other way to store, so I had to write everything again from zero every time. Modern computers have what we call secondary storage. That can be hard disk or some different technology, but the philosophy is the same. This is a big storage, which is cheap but slow. So this is fast, expensive, and bad memory. It loses the information when you turn off the electricity. This is the contrary. This is slow, cheap, but can keep information for long term. I will not say forever, but for many, many years. And the new part that is kind of new in this thing is connection to the network. Modern computers, all of them connect to the network. So this is more or less the scheme that we have today. This is a very simplified, and if you look, your telephone has interface, has storage. The storage is not a physical disk, but there is some kind of flash memory. There are different technology, but the parts are essentially the same. The network in your telephone can be the cellular network, but this pretty much covers all the computers that we connect every day. We interact every day. Now, okay, you already explained this thing. This is the central process, what people call the brain. And here is when the process happens. And people pay a lot of this. This is the Intel or the part that if you pay more, you get faster computer. That's essentially one of the people pay if you want to do things faster. Now, the part that I want to focus is this, memory. The primary memory is also called random access memory, that is RAM, random access. It stores the information that you want to use, but is small, and they are expensive, and they are volatile. So first, just to have an idea, just imagine that this is the memory is a collection of little boxes, and in every box you can store one number, okay? So well, I already explained you, the reason why we have a secondary memory is because the RAM can lose all the data if the electricity go off. And so we have a secondary kind of storage. Now, the point is this. What we will do, you will read this part anyway, but I already told you. By the way, hard disks are called this because they are physically a disk of a solid material. There is another technology of soft disk, but today you probably have a USB stick, or you store in the cloud, in Dropbox or Google Cloud, or I don't know. There are many ways. So secondary memory can also be cloud storage, which is, by the way, hard disk in someone else's computer. The point is that the main trade-off is between big amount, long-term storage, and speed. We essentially spend a lot of time in this problem. This is the main problem, and it will take us some time to be aware of this thing. We will be moving information between the storage and the main memory, between the secondary and the main memory. So maybe some of you saw this before. The idea is this. The primary memory is like your desk. If you want to see a book, you have to open in your desk. The secondary storage is like the bookshelf. If you see in my bag, that is my secondary storage. I store my books there, but I cannot read them. If I want to read my book, I have to take it one here and open here in my desk. Now my desk can hold, I don't know, 3-4 books, so I can read a limited amount of books. If I want to read another book, I have to take the old book, put in the storage, and take a new one and open here. That movement between the storage, the bookshelf, and the desk is what we are going to be doing most of the time. Okay, the unit of measuring of storage is called byte. As I say, memory in the disk and in the main memory is a series of boxes. Every box can store limited amount. There is a technical reason that makes that the best option is to store number between 0 and 255. If you are curious, we can talk about later. It's not important, the technical reason. The only thing that you have to know is that The basic unit of storage is a number between more or less 0 and 250. And this number can represent many things. In particular, 1 byte corresponds to 1 letter. That is the reason why it's a good size. 1 byte, 1 letter. Ideally, 1 byte, 1 letter. So we measure the storage of your computer in bytes, and every byte can be 1 letter. So this is the thing that you have to keep in mind. 1 byte, 1 letter, an integer between 0 and 255. Okay? I mean, you don't need to remember the two. Well, it's good to know, people. But the point is a small number. You cannot store, if you want to store bigger number, you need more bytes. If you want to store decimal, like 3.1415592, you need more bytes. Exercise now. How much memory you have in your computer, or in your telephone. So, for example, that is not a very easy question, to be honest. For example, I have this telephone that sometimes works, sometimes doesn't work. And like any computer, this computer has two kinds of memory. Fast memory, the RAM, and a slow memory, which is the storage, the secondary storage. How much we have in each one? Well, it's not so easy to know. For example, I know the storage of this computer. Maybe I can see here. Well, maybe I can show it later. This capacity says 64 gigabytes. That is the storage of this computer, but I don't know what is the RAM. When you buy a new computer, one of the main things that they improve is the primary memory, not the secondary memory. So the exercise, and you can answer this, I don't know. Let's answer in the chat. You should know what is the capacity of your computer, what is the storage, and what is the memory, the RAM, the primary memory and the secondary memory. Why this is important? Because the amount of, well, you need to know how much you can store. For example, if you want to download work in the human genome, for example, can you have the human genome in your computer? Well, first you have to ask if you can store it in the hard disk, in the secondary memory. Second, you want to know if you can load it in the computer memory, in the primary memory, in the RAM. Maybe your computer can store it in the hard disk, but not in the RAM. So if you cannot store it in the RAM, you need to handle it in a different way. By the way, the difference is super important, because if the data is small, you can do everything in primary memory, in RAM, and it's very fast. If no, you have to use the disk, and that is much slower. So these kind of questions are important. So in practice, this means, in real practical terms, it means that if you buy a computer, try to get a lot of RAM. Having a lot of RAM is usually the most important thing to make the computer fast. Because the main bottleneck, the main problem is moving data from the hard disk to the main memory. If you have a lot of main memory, you put everything there and it's very fast. Otherwise, you need to use the hard disk. I don't care very much if you are not very sure, but it's a question that you should be thinking about. You should know. I mean, it's like if you have a car, for example, maybe there are many technical things that some people care, some people don't care. In this case, this is not a very technical thing. It's something like you need to know what kind of gasoline. If you go to the benzene and you have, the 93, 95, 98, this kind of things are important if you have a car. You need to, for example, to know the pressure of the wheels. The elastic needs some pressure. So you need to know these things. If you don't know, you need to know. It's not that you are going to use it every time, but you cannot go by life without knowing that thing. for example, Recep say that he has the secondary storage has two technologies. One is HDD and the other is SSD. I'm not going to enter in detail for this. 16 gigabytes of RAM. Well, enough, depending for what. Later I will tell you some problems that are require a lot of memory. For example, in bioinformatics, one of the problems is DNA assembly. And you probably know there's the kind of the new generation, NGS, new generation sequencer that are very cheap and they produce a lot of data. The main problem is memory. Usually with the new generation, you need, I don't know, 5,000 gigabytes, 5,000, no, 500. 5,000, 1,000 gigabytes. You need a lot of RAM for assembly. For other problems, it's not so important. Here, for example, I am working with a colleague in a project, and they give me all the data of the project in this disk, a lot of sequences. So obviously, this is not a question that I'm going to ask in the computer, but a typical exam question or homework question is this. How many pictures can you store in your computer? How many hours of video? Assuming, for example, if you have a picture, for example, I told you microarrays. You know microarray, no? It's a technology for measuring the concentration of DNA. Microarrays take what they take. Microarrays are you scan the experiment after overnight hybridization. You get a picture that is typically, I don't know, 10,000 by 10,000 and 2 bytes per pixel. They have a high resolution in the colors, so they have 2 bytes red, 2 bytes green. So they are kind of big files. And the question is how many of that can you store? For example, if you have a USB stick, can you store everything in the USB stick? Can you copy the file? Or if I get the genome of a new plant, for example, I am working with someone and they want to give me the genome of a plant. Can I store it? If I want, for example, a metagenomic sample, and I suspect that in the metagenomic sample there are 10,000 bacteria. Can I store the genome of 10,000 bacteria in my computer? That kind of questions are good questions for an exam, but they are so practical, because it's kind of, I don't know, like there is a basic level of knowledge of the world that, I mean, you don't say something silly, like, I don't know. You know the typical joke that the people who want to send, in all time people have the letters, and the letter you can put money inside or you can send a package with food or whatever. And then they invented a telegraph, and you can send a telegram with the information. But people say, can I send food with the telegram? Can I send a physical thing? No, you cannot. So this is the kind of question that if you don't know, it looks silly. So if you say that I can store everything in my computer and your computer has not the memory, it is an issue. And I will turn off my video. So this was the memory size. Good question. Well, do you have any question? A silly question. What? RAM. Okay, bacteria don't have RAM. So, but I think the question is more like, what is the amount of memory of a typical bacteria? It's a very good question. I mean, it's not asked in a correct way because RAM is a technical term that corresponds to a physical thing, but I understand that you ask amount of. A typical bacteria, I will say, has in between, let's say, 1 million and 6 million base pairs. E. coli has 4 million. In my mind, I will say 3 million, but let's say for 5 million. Just to fix idea, typical bacteria, if you had to choose, I would say 5 million nucleotides. Now, every nucleotide has 4 values, no? So you have A, C, G, and T. Therefore, you can combine them, and if you want to do it very efficiently, you essentially say something like, what will you say? 4 nucleotides fit in 1 byte. So 4 base pair equal 1 byte, if you do it efficiently. So typical bacteria, 5 base pair, 5 million. Therefore, I will say it's something like 1.25 megabyte. Yeah, so grosso modo, 1 bacteria is 1 megabyte, grosso modo. Oh, by the way, remember that we say that we represent things with numbers. That is the most efficient. The naive, the simple, in a simple case, if that is in fact what we most in the simple case, I will say that you have 1 base pair equal 1 byte. It's not the most efficient, but it's the most simple way. Okay. Because if you compress them, they are harder to find. I mean, you take 1 byte and you open 4 letters. The best way, the simple way, is 1 base pair, 1 letter. In that case, 5 million base pairs is 5 megabytes. Now, I give you a question back. What is the size of a human genome? Human genome, if I'm not wrong, is 30. I may be wrong by 10. I'm not sure. Human 30,000 mega base pair is essentially 1,000 or to 10,000. I'm not complete. I think it's 30,000 mega base pairs. And plant can be much more. You know, the plant genomes are usually much bigger. If you work with barley or I mean, in the department we work a lot with plants, and they are the hardest genomes. They have another technical problem. I will not tell very much, but they are tetraploid or hexaploid, meaning that you have many copies of more or less the same chromosome, but it's not exactly the same. If it was the same, no problem, but they are very much similar. The idea of using, it's an interesting idea, that if we can store, use bacteria to store information. Yeah, it's a good question. This is the kind of thing that better if we talk with the microphone, you know, that is why we have microphone. Okay, let's do something. Let's make another break. And if you want to talk about this, we talk now. We still have a little more time, and I have another slide to show you. So, but I will try to, the next one, I want to make it fast. But so let's do this. 15 minutes of break. I will be here. If you want to talk, turn on your microphone, hopefully your camera. If no, come back in at 2 p.m. Okay?